In one of the previous videos, we saw that at constant volume, as in when delta V is equal to 0, the energy change is equal to heat, because W in this case is 0. So delta E is just the heat. Now, if we were doing chemical reactions, if we were interested in chemical reactions at not constant volume but constant pressure. So constant pressure reactions are the ones that we conduct on in open vessels, open reaction vessels. Or if you had to have a practical example, the practical example would be burning of natural gas. Burning of natural gas, right? Such reactions are reactions at constant pressure. When constant pressure is involved, delta E will be Q plus W. This will be equal to Q minus P delta V, because pressure volume work is P delta V, negative P delta V. So if we are interested explicitly in the heat of such reactions, then heat will be equal to delta E plus P delta V. Heat in such cases is change in enthalpy. Heat in such cases during constant pressure reaction, that's what we mean. During constant pressure reaction situation, heat involved in the reaction is represented as change in enthalpy. Change in enthalpy. Change in enthalpy, and this is equal to delta E plus P delta V. Now, if this delta H is equal to delta E plus P delta V, numerically, what are some of the aspects that we have to keep in mind? You have to remember that delta E is the difference in the change in internal energy. Change in internal energy, meaning here both potential and kinetic energy both are involved, right? Internal energy is the sum of energy. So change in internal energy means change in, or delta E is a measure of all energy exchanged to the surrounding, whereas delta H is just the heat aspect of it. Delta H is a measure of only heat exchange, just the heat exchange, and this does not involve the work aspect of delta E. Now, a positive sign of delta H, if delta H is positive, such a reaction is known as endothermic reaction. Such a reaction is known as endothermic reaction. And what is happening in endothermic reaction? In endothermic reaction, heat flows into the system as the reaction occurs. Heat is absorbed by the system as the reaction occurs. Now, what if delta H is a negative number? If delta H is a negative number, such reaction is known as an exothermic reaction. exothermic reaction and heat is emitted. Heat is given off to the surroundings. Heat is given off to the surroundings. Primarily, these are the two differences between endothermic and exothermic reactions. For example, if you see a reaction that looks like this, C3H8 plus 5 oxygens yields 3 carbon dioxide and 4 water, and delta H for this reaction is given as negative 2044 kilojoules. What does this mean? This means that for every 1 mole of C3H8 is propane. So for every 1 mole of propane to react with 5 moles of oxygen to yield 3 moles of carbon dioxide and 4 moles of water, there is a release of 2044 kilojoules of energy, of heat. So you can say, and you can use this as a conversion factor, 1 mole of C3H8, when it goes through combustion, it releases 2044 kilojoules of energy, and you can put a negative to indicate that it is a release. Now, what is the molar mass of C3H8? C3H8 molar mass is 12.01 times 3 plus 1.00 times 8, 1.008 times 8, which is equal to 44.09 grams per mole. That's the molar mass of C3H8. So this conversion factor can also be written as 44.09 grams of propane, when it goes through combustion, releases 2044 kilojoules of energy. Now, if a question is asked, what is the heat associated with, associated with combustion of 13.2 kilograms of propane. 13.2 kilograms of propane. We know what is the heat associated with 44.09 grams of propane. Now, we are asked to calculate what is the heat associated with 13.2 kilograms of propane. So, the way you are going to work on this will be 13.2 kilograms of propane is equal to 13200 grams of propane, right? And so 13200 grams of propane multiplied by every 44.09 grams of propane is associated with negative 2044 kilojoules of heat. So this will come out to be negative 6.12 times 10 raised to 5 kilojoules of heat. What are the important aspects of relationships involving delta H, right? So if we take a general reaction, any general reaction, A plus 2B yields C, and the delta H value for this is H1, some number H1. If we multiply this entire reaction by 2, meaning 2A plus 4B yields 2C, what will be the delta H for this one? Delta H for this reaction will be 2 times H1, because when you multiply the reaction, you should also multiply the delta H. If chemical reaction is reversed, for example, if we had the same reaction considering A plus 2B yields C, delta H is H1. What would be the delta H for C yields A plus 2B? Delta H in this case will be negative H1. So if the reaction gets reversed, the sign of delta H gets flipped. So in this case, it was an endothermic reaction, and when you flip it, it becomes the reverse of a reaction will become, reverse of that reaction will become an exothermic reaction. So if you reverse the reaction, the type of the reaction will change because the sign of the delta H is changing. If a reaction can be carried out in multiple steps, so again considering the reaction A plus 2B yields C, and another reaction C yields 2D. We know the delta H's of these two. For example, delta H for this one, the first reaction is H1, and delta H for this reaction is H2. If you add these two reactions, you get A plus 2B plus C yields C plus 2D. And delta H for this reaction would be H1 plus H2. In this case, C is found on both the sides of the reaction, so it gets cancelled out. So A plus 2B yields 2D, and the delta H for this reaction is H1 plus H2. Because you added these two reactions, you will add the delta H numbers also. So if a reaction is added to another reaction, the delta H's will also be added to find the overall delta H for the overall reaction. And an important aspect of this is known as, or important consequence of this, or important point about this third relationship, Hess law. Change in enthalpy for stepwise process. Change in enthalpy for stepwise process is the sum of enthalpy changes of the steps. Now, numerical problems for Hess law are very important. So, for example, given C3H8 plus 5O2 yields 3CO2 plus 4H2O. Delta H is negative 2043 kilojoules. Also given C solid, carbon solid, graphite plus oxygen yields carbon dioxide gas. Delta H for this reaction is negative 393.5 kilojoules. Two hydrogen gas plus 1 mole of oxygen gas yields 2 moles of water, and delta H is given as negative 483.6 kilojoules. What would be the delta H of 3 carbon solid plus 4 hydrogen gas yields C3H8 gas? What would be the delta H for this? So use these three reactions to determine the delta H for this reaction. So this is our reaction that we are interested in. So we have to manipulate these three reactions, given reactions 1, 2 and 3. We have to manipulate these three reactions to come up with this reaction. So in the reaction that we're interested in, there is 4 hydrogen moles. In this case, I'm seeing 2 hydrogen moles right here. So to get to 4 hydrogen moles, we shall multiply equation number 3 with 2. So multiply 3 with 2. So you will get with that 4H2 plus 2O2 plus 2O2 yields 4H2O gas, and delta H will be also multiplied with 967, negative 967.2. In the reaction that we're interested in, we're seeing that there are 3 carbon solids on the reactant. So let's multiply equation 2 with 3. So we will get 3 carbon solids plus 3 moles of oxygen gas yields 3 moles of carbon dioxide gas, and delta H will be 393.5 multiplied by 3, which will be 1180, negative 1180.5. We're also interested in having propane on the product side. In the given reaction number 1, we have propane on the reactant side. So we're going to flip reaction 1. Reaction 1, flip or reverse, or write it as 3CO2 plus 4H2O. This is gas in the given problem. All are gases. So CO2, H2O yields C3H8 plus 5O2, and delta H will be positive 2043 kilojoules. Now add all these three reactions. When you add all these three reactions, you will get 4H2 plus 2O2 plus 3C plus 3O2 plus 3CO2 plus 4H2O. These are all the reactants, yields 4H2O plus 3CO2 plus C3H8 plus 5 oxygen gas, and delta H will turn out to be 2043 minus 1180.5 minus 967.2, and that will be negative 104.7, negative 104.7, which is equal to, because there is no digits after decimal, negative 105 kilojoules. And what is our reaction that we're seeing here? Carbon dioxide is 3 moles on both the sides, so it gets cancelled. I cancelled the wrong thing, so let me erase this first. This is 3O2. Okay. Carbon dioxide cancels on both the sides. Water vapor cancels on both the sides. 2 oxygen plus 3 oxygen is equal to 5 oxygen, and we have 5 oxygen, so that cancels. So what are we left with? We are left with 4H2 plus 3C yields C3H8 gas with a delta H of negative 105, and this is what we were interested in to begin with, if you look at the reaction that we were interested in. So you have to manipulate the given equations to get the reaction that we are interested in.